So good morning, thank you for being here. So it's a pleasure for me to introduce Hila Peleg, who is a student, a PhD student of Muli Sagiv and Eran Yava at Tel Aviv University. So she's going to talk us about, I think, her SAS paper she will present next week. And so Hila is expert in programming languages, but also in literature. So she owns a degree in comparative literature, and she's also an expert of databases. Yesterday she helped me a lot with database for Clouseau. So, yeah, thank you.
Thank you. So I'd like to talk to you a little bit about specification mining. We live as programmers in a world of APIs. Most of the time when you need to do something, you don't write it from scratch. You're given some library and figure out how to use it. If you're fortunate, it's well documented, the API is clear. Most of the time, we're not that fortunate. And then we have to figure out, what are we going to do? So what we would like to offer is the ability to look at code and get from it a type state that you can use, a temporal specification, which is you should do this, then this, then this. Find out the correct sequence to use in order to do stuff. In the case of this example here, I'd like to get a connection from JDBC, the Java database library. I'd like to prepare a statement. And then I'd like to either execute an update or set a parameter, and then close. But now we start wondering, if I want to look at an example, what example should I be looking at? If I look up SQL connection, I'm going to get, I think 60,000 results is a nice lower bound. I'm going to get a lot more. And more results are added every day. So which example am I going to pick to look at as a programmer that just wants an example to figure out what I should do? Well, I could pick the first result I get, or a random one. But that's not good enough. For example, what if the example I just picked randomly has a bug in it? So first of all, this little example has two problems. First of all, I'm committing on a connection that's in auto-commit mode. That is, if I commit on it, I'm going to get an error. And second of all, and this is actually best practice and not so much a bug, I'm using prepared statement, which compiles the statement and leaves me with the sort of unnamed stored procedure for something that I'm going to use once and throw away. And you usually don't want to do that. So we'd like to be able to pick an example that's both correct, doesn't have bugs, and as close to the best practice as possible. Another problem is, what if the example I'm looking at has pieces of information missing? So you can see here that we're actually doing the correct thing now. We're opening a connection, we're starting a transaction, we're using a statement that isn't prepared, and we're executing it. But we're starting a transaction with some external code that I don't have access to, some helper function and some helper class that I'm going to have to go looking for now. And I might not even find. So I'd like to use all the examples I can find. I'd like to use every piece of code on the internet that uses JDBC, throw it into some little magic black box, and use that to find a canonical example, which is an example I know to be correct, to complete the partial examples that have missing parts. I'd like to search what I got to say, I want to use update. What do I have to do to use update? And I'd like to take the code that I wrote and get it validated. So what do we need to do in order to be able to do all of these? Well, first of all, we need to be able to analyze a single code example. We need to get the histories of API usage, where a history is the sequence of methods in that call from that example. I need to do that ad nauseum until I'm out of examples. I need to create an index out of all the examples that I got. And I need to be able to use that for searching and for verification. So let's start with looking at a single example. The concrete history, which is the actual sequence of calls in a piece of code for an API object. I have the something object that I'm tracking, gets FG and age called, and I get myself a concrete history with FG and age, which is swell so far, except now things get complicated. First of all, sometimes I have related objects. In this case, there's actually only one object, but if I simply looked at variable names, I'm going to see two. So I'd like to do a little heap analysis and make sure I see them as one object and still get the one history for both of them. Sometimes objects are also related because they're part of a creation chain. I have my something object for which I do something, and then I use it to create something else for which I do something else. And I like to see that as one temporal chain of events. Also, sometimes I have, like we saw before, missing code. Something happens to my object, which possibly changes its state, but I don't have access to this code. So I'd like to take that and mark that as my little unknown question mark over here. And of course, I have my unbounded cases of loops, where I both have an unbounded length for history and an unbounded number of histories, because I have every option, every number of iterations for the loop here. So I'm going to need an abstraction. First of all, I'm going to need to be able to group all my API calls for an object. So for that, we do heap abstraction and we track creation chains. I'm going to need to be able to represent in a bounded manner my loops, and I'm going to be to have to represent my unknowns. For that, we're going to use variables. And just for the sake of convention, we're going to use the higher end of the alphabet for variables, the lower end of the alphabet for concrete letters. So this abstraction is DSAS, deterministic symbolic automata. You will forgive me my basically one Greek slide in this presentation. A DSA is very much like a DFA. That is, we have our alphabet, we have our set of states, we have our transition function, our initial state, our accepting states, and we also have a set of variables, which are unknown bits. And our transition function can either transition on a concrete letter or on a variable. Now, the way that a DFA has a language, a DSA has a symbolic language, where we have words that are either concrete, just made up of letters of the alphabet, or symbolic words that are made up of both letters and variables. So for example, here we have A, which gets to an accepting state, A, B, X, C, D, and then as many iterations of the loop. Just like regular automata. And now we have assignments, because we can't talk about variables and not talk about what we're going to assign into them. An assignment is going to map non-empty symbolic language, not necessarily concrete, could be symbolic, into a variable. So for instance, we have this DSA, and we want to map d EYD star into x. So we basically take the little automaton for what we're assigning and stick it instead of the variable. Now, you're probably wondering about what's around x in that assignment. And that's our assignment context. Because sometimes we're not just going to want to replace x. Sometimes we want to replace x in a slightly different manner, depending what's before it and what's after it. So SW1 and SW2, two symbolic words, are the context of our assignment. So for instance, for this automaton here, we're going to say that if x is followed by b, we're going to assign db. And if x is followed by c, we're going to assign ec. And the result of our assignment is going to look like that. So what we did is we took the split point and pulled it back 1 or 2 or 3 nodes. And we can do the exact same thing with incoming context. And if you think about it as something that represents code, basically what we did here is say, there's a branching in the code. This is maybe a conditional. What we did is assign to the beginning of each branch. We say, the beginning of the if has this, the beginning of the else has that. So now that we have our representation, we can create it out of code, we can assign to it. It's time to start creating our abstract domain so that we can actually do analyses with it. So a DSA is the natural representation for a set of histories, which is great. It looks like a type state. You can show it to people. You can use it to verify just like a type state. Now we need a partial order so that we can create a lattice. And we want to capture this order in a sort of dual ambivalent manner. Precision and partialness, which I'm getting to in just a second. And we want to show some other operations that are going to be useful later in the analysis, mostly for query matching. So we want order between DSAs. Since we're looking at automata, you say, OK, language inclusion. You have automata. You order them by language inclusion. That wouldn't always work when you have symbolic automata. For instance, these two automata here, the one on the left, if you think about it, is actually related in a manner to the one on the right. Since if you assign either A or B into X, you're going to get something that actually has some relation to this one here. But if you simply look at language inclusion, you're going to say, oh, well, I don't have language inclusion. I don't have order between these two at all. That's no good. So we want to look at the notion of partialness. A word is less partial or more complete than another word if it represents a more concrete scenario. Now, intuitively, we would say a word is more partial if it has more free variables. But more formally, we want to say that a word is more partial if for each assignment to one, there is an assignment to the other that gives us word equality. So for instance, if we look at these two over here that are very obviously partial, for the empty assignment to ADB, that's basically each assignment that we can have here, there is an assignment, x equals d, that's going to give us word equality. So we say that AXB is partial to ADB. So in order to take this concept of precision into account, we're going to create this compound order along two axes. First of all, we have precision, which is what we call the principle behind language inclusion. The more words are accepted by the DSA, the less precise it is, or the more complete it is. And partialness of the individual words against the words in the other DSA. So intuitively, we're going to say a DSA is smaller if it's more precise and more partial. And if you think about it, precision is the classic upwards direction of a lattice like you're used to it. Partialness makes it interesting. Keep that in mind. We're going to look at that in just a second. So if we look at these three DSAs as an example, right before we define it formally, that go from smallest on the bottom to largest on the top. The middle one versus the top one, we have just precision. We have an extra branch that gives us a larger language. And if you look at the lowest one against the middle one, then we have just partialness in play. We have AX, BY, which has the extra variable is more partial. For any assignment to X, we have the same assignment to X and the empty word assigned to Y to get language equality. And transitively, the lowest one is smallest than the top one, because we have, once you get that assignment of whatever you assign to X, you assign to X, and the empty word to Y, you get language inclusion with a larger language on top. Now, the less precise you are, the more behaviors you describe. That's, the natural thing that you're used to seeing in a lattice. But the more partial you are, the more behavior you describe. Because here we can take Y and assign whatever we want. It's this ambivalence of the direction of our order, which is, I think, pretty neat, but at times confusing. The further you go up, the more concrete behaviors we're talking about. The further down you go, the more possible behaviors we're talking about. Now, formally, we say A1 is less than A2 if for every concrete assignment to A2, we have a concrete assignment to A1. Concrete assignments are assignments to give us a fully concrete language with no symbols left, where we have language inclusion. Now, we want to talk in completely concrete assignments here, so that we can collapse ourselves to plain language inclusion with nothing that gets in the way. So, for instance, if we have these two here, for the empty assignment here, we have the assignment where X is equal to A, and we get language inclusion. So we can say that the left automaton is less than the right automaton. Now, this is all well and good, except if you can't calculate it, it doesn't help anyone. So we're going to calculate it through simulation. We want to take the notion of simulating DFAs to find language inclusion, which you might be familiar with, and adapt it to the case in which we have a symbolic language. We want to find pairs of states, a state from the automaton that we suspect to be smaller versus a set of states from the automaton that we suspect to be larger that are going to give us a witness to there being an inclusion. So we're going to collect possible candidates looking at the outgoing transitions. Now, since language inclusion regular DFA simulation already gives us the notion of precision, all we have to do is add in there the notion of partialness, the fact that a variable can basically eat up a whole lot of transitions from where we are at the moment. So let's do that through a little example for these two. We suspect that the one on the top is smaller, and the one on the bottom is larger. And now the definition for simulation, for the relation itself, is very intuitively recursive. But we're actually going to do the forward-only version, since we're very proud to have a polynomial algorithm for that. So we're going to start with the initial states. We're going to take them, we're going to add them to our relation. And as long as we can keep moving forward from the initial state versus the initial state and not get stuck and still have all the states of the alleged smaller DSA represented, if we've managed to encompass them all, then we have a simulation. We have a witness to every word here having a larger word here. So we're going to try to leave our set of initial states. So in the allegedly smaller DSA, we leave 0 with A. So do we have a way to leave our set of states, which is just 0, with A? Yes, we do. So we go to 1 and 1 and add it to our relation. Now, the same thing with leaving 1 and 1 with B. We can do that. That's great. Now it becomes interesting, because we want to leave 2, the green 2, and we leave that with x. X is a variable. So what are we going to do? The move from 2 to 3 can have anything assigned to it. So what I'm going to say is, OK, well, it can have anything from the empty word, so staying in place on the lower automaton, to basically the rest of my language. So I'm going to take everything that's reachable from where I am. So all the states from 2 to 6. Now when I want to move out from the green 3 and go to the green 4, and I'm back with a concrete transition, I'm looking for a way to leave any of the states that I have here with the same concrete transition. Now, I could theoretically have more than one transition that does that. I could keep collecting a set here. But it just so happens that there is only one C in that group, and that's the C going from the red 3 to the red 4. So I have 4 and 4. Now I move on with D just like I did before, and with B. Now you'll notice I've gone around the loop in the green automaton, but I'm still adding pairs that I haven't seen before, so I keep going. Now I have X and X, moving from 2 to 3 in the green one and 6 to 3 in the red one. But they're not actually the same X. Right, there's an unknown in my bottom DSA, but it's a different unknown, or it might be. So I do what I did before. I say, well, I could be assigning an empty word. I could be assigning a different variable. And I could be assigning, well, basically anything that I have left over. So I say anything that's reachable from the red 6, I put in my simulation. Now, my actual simulation, my minimal simulation, might be a slightly smaller set, but right now I'm over approximating to make sure that if there is a simulation, I'll get to the end. So yet again, I want to leave the green 3 to the green 4 with a C, and that's the C from the red 3 to the red 4. So now I'll be adding 4 and 4, which I already have in my simulation. Now, the simulation from any point going forward is always going to be the same, so I know I can stop. Now, I've represented every state of my smaller automaton, and I didn't get stuck in any way. So I can say that the upper DSA is less than the lower DSA.
You don't understand. You haven't considered final states at all in the.
I consider final states. I basically look to see that every final state has a final state paired with it in my set. So if you'll see 1 and 1, which are both final, and 1 again is paired with 5, which is a final state, which basically says if you think of the simulation of giving me a path to get a word out of the lower automaton to match the word that I'm going through, then I know that if my set has a final state, I have a way to get to a word that matches and is also accepted. Now, this order that we are looking at is a preorder. It's transitive, which is great. It's reflexive, which is swell. It's not anti-symmetric. So if you look at the left automaton, it's larger than the right automaton because it has the extra branch, it has the larger language. But it's also less than the right automaton because it's more partial. It has the extra variable, the extra degree of freedom. So, but we want a lattice, so we need a partial order.
Why do you want the lattice? Why you want the lattice?
Because I want an analysis.
Why? But you don't need a lattice to analysis.
I want join, for starters.
Not necessary.
Well, I need it. I'm going to. I want join because I want to be able to mash together my gazillion code examples and get something that's representative.
So you want the best. So you want the best one, not one.
I want.
You want the best.
I want the least.
The least upper bound. Okay.
Yeah.
That's
I really, really want join. So, and in fact, I want something slightly better than join. So, but that's in just a second. So we need a partial order. What do we do? Well, it's actually not that hard. We go to equivalence classes, which is simple in theory, computationally not that fun. So in the case of equivalent automata, like we just saw, we're going to put them in the same equivalent class. And in this case, now we have a partial order between our equivalence classes. So now we're ready to define join, which is what we were working up to all along. We're going to take the union, just like DFA union, of our two automata. It's, well, actually almost like a DFA union if we're moving past two variables in order to do the union. We're going to collapse them together. And this is now a representative of the equivalence class of the least upper bound. Yay. So we have a joined semi-lattice. So we're very, very glad. But we want to really compute join. And more than that, we want to be able to get a result for join that's informative. Because if we start with the union operation, then we might get something that's that has redundant paths. And we want to look at a most complete representative, or the most complete that we can get from the equivalence class that we're now representing. So we want to find duplicate words in our result. So either two words that are equivalent that got into our automaton, or a word that's less than another word in the same language.
So you just want to minimize the symbolic automata.
Well, it's not quite minimization, because minimization, or rather, the way that you usually look at minimization won't quite cut it. Because I'm not only looking for equivalent words. If I was only looking for equivalent words, minimization would be enough. I'd say, well, if I have differently named variables, I'll treat it as normal minimization, and that's fine. But I'm also looking for words that are subsumed. I have two words in the same automaton where one is less than the other. One is partial to the other. And I'd like to only keep the less partial one of the two. So we call this consolidation, and it's just a little harder to do than minimization. And the best example, which is where regular minimization won't quite cut it, is this one, where we'd like to have the extra path of AXB, which is partial to ADB. So it's so we don't want it anymore. We feel it's represented well enough in the more concrete path, in the more concrete word in the language. So we'd like to lose it. We'd like to throw it out. So this is more of a language operation than it is an automaton operation, which is why minimization isn't enough. We say, oh, our language here has redundancy. We'd like to lose it.
You want to lose symbolic? You want to lose the more partial?
We want to lose the more partial. We want to find the most complete representative that we can get. And if we have two words where one is partial to the other, in our search for the more complete representative, we're going to slice out the more partial words. If you think about it in code examples for a second, if my language is open, read, and close, and then it also has open, I have no idea what's in there, close, well, I have that answer. It's open, read, and close. Sure, it might be open, start a connection to the database, close. But if I have enough examples on hand, I know I'm going to get at least something to put in that variable. And I can just slice the variable. The variable is there for a case that I have no better answer to give. So this is consolidation, which we do for answering queries. Oh, yeah.
How does it work?
Very, very slowly, unfortunately.
You just determinize using access everything pretty much?
Well, definition-wise, which is why it's very, very slow, I look at the language and start throwing out redundant words. When I try to do this, I have a heuristic for getting a better automaton. But of course, once you add loops into the mix, then you might throw out, you might have a path outside the loop that's redundant to the one in the loop. And it becomes, shall we say, computationally fun.
So again, this is not a problem because you want to have a least upper bound somehow.
I already have a least upper
Yeah,
bound.
but computing it, it's expensive.
Well,
so because somehow you want to have some kind of canonical representative for it, so you spend a lot of time getting the canonical
Yeah.
representative and then doing the other operations.
Yeah.
And this is somehow non-hysteric analysis, and if you're going to do all this eager work, you're going to die. So that's I'm wondering if you measure the other way around. Don't go for this eager approach. Give up the least upper bound, just keep an upper bound.
No, I
then
already
use
have
it
the
when you
least
want.
upper bound. I mean, my union of two automata is already the least upper bound.
Just keep it.
Yeah, I can,
So
I can
you
keep
try
it.
just keeping it and not doing this work. So you know
Well,
how it's going to work.
I can do that, but the reason I want to do this is that later I want to start answering queries. And when I answer queries, I'd like to have the most informative representative of my least upper bound. Because if I have a lot of redundancy in the database I'm searching against, I'm not going to give you very good answers to your queries. So we have a...
I have a quick question.
Oh.
Because I came late, I have a silly question, but on the last slide, when you show the example,
Yeah.
What is the reason that you throw away, for example, the string ABB, which is not accepted by the right-hand side, but it's accepted by the left-hand side? Why are you considering this as sort of information you don't want?
ADB
So, for
is...
example, the string X can be anything, right? It can be any string.
X can be anything.
But you don't want it because it's not covered by the rest of it?
I don't want it because it... the reason I had it to begin with is because there was something there that I didn't have access to. So let's just do this. This is going to be a lot easier.
figure it out in my head.
Okay. Every once in a while, when I'm looking at code, since I'm not looking at complete programs, I'm looking at partial code, I'm going to come across something that might alter the state of my object, but I don't have access to. I have no idea what goes on in the transmorgify function, because I don't have its code. But since it takes my object, it might alter its state. It might be important. So I put a little marker there for something goes on there I don't know. These are my variables. So once I start joining together a lot of examples, and I have more and more complete information, if I have a path that says, oh, I know what's there, then I can lose the path that says something goes on there and I don't know. I'd like to only still be keeping these variables at the very, very end if I looked at all the code and I still don't know what goes there.
Good.
So.
Thanks.
OK. So we took a bunch of examples. We analyzed them. We mashed them together. We consolidated them. We're very happy. We have a database representing the behavior of our API. And as you can see, there's still one little path there where we couldn't get more complete information. We, of course, aspire to a completely concrete database, but we're realistic. And now we'd like to start asking questions, or allow the user to ask questions. Like, I want to use E. I want to call that method. What's the right thing to do around it so I use it correctly? Because if you think of yourselves as programmers who get told, yeah, use JDBC, it'll work. Then you say, OK, well, I want to read from a result set. What do I do before and after? I have no idea yet. So first of all, we turn our query into a DSA. And this DSA, if we have an answer to the query, is going to be less than or more partial than our database. And we look for an assignment that will give us language inclusion. That is, turn our query into a piece of the larger automaton. In our case, if we take x equals to a and y equals to c with no context, we're just going to get that one branch that has a, e, c, which is what we want. Now, this is a process that we call unknown elimination. And if consolidation was not efficient, this is even worse. So if we have two automata which are symbolically included, and if we have a result, our query is symbolically included, we know that the concrete parts match up. We have the concrete parts of the smaller automaton in the larger automaton. And we simply have bits that go in the variables to match it up. So we want to find out the not necessarily concrete parts of the larger automaton to go in the variables. We already have the simulation, which gives us an over-approximation of what should go in the variables to match them up, which is nice, because we already ran the simulation to make sure that they're symbolically included to begin with. So we want to use that to figure out what's the more minimal assignment that should go in there. Of course, this is very, very easy when you don't have context. You basically slice off everything that's already in use later, and you get a very small set of states that match up. When you have context, this gets very, very difficult. Because an assignment can have both an incoming and an outgoing context, like we saw before. And this means that we have to take our simulation and start computing incoming and outgoing contexts to each transition with variable. And we have to check different lengths of context because we're not limiting the length of the context, and try to find a consistent assignment for each of the variables from that. This is, again, needless to say, rather inefficient, but necessary in order to allow context. So let's put everything together and see what we do. So we like to perform an analysis with everything we've got. We want to take a bunch of programs, or partial programs. We want to mine the API usage out of each one of them. We want to join them together to create our database and consolidate that result to have a more informative database. And we like to use that database with unknown elimination to answer queries. So a bunch of program snippets. We have these use an imaginary socket API. So program A creates a new socket, configures it using a method that we have no access to, connects, sends, and closes. Program B has a method that reads as long as it can from a socket that it gets, and a method that sends and closes a buffer that it gets from the outside. So we mine each one for API usage. So in our top automaton, we have the little unknown for the configure method that we have no access to. Something goes there, we're not sure what. The bottom one has the loop folded on itself the way that we saw before. And now you'll notice that B1 and B2 have unknowns at the beginning and the end. This is because this is usage from a method that gets the socket from outside. We don't know what happened to the socket before. We don't know what happens to the socket later. So, and it might, of course, be important to its state. So we leave them as unknowns. We want to join them to create a database. Now, just to make it quicker, I'm going to do a slightly consolidating version as I join. Because I know that B1 is less than A1. Since we have the send and the close matching up, and if we assign an empty string there and the entire beginning of the automaton to there, we'll have word equality. So their join is just going to collapse to the larger one, and that just leaves me with A1 joined with B2, which is this here, which I can't consolidate any further. I don't have any redundancies left. So at least there's some portion of consolidation that's easy to do. So that's great for me. And we want to take that and use that to answer queries. Now, since we started saying we want to look at all of the code in the internet, we have to ask ourselves a very quick question. Is all the code in the internet right? Well, we started out by saying no, so that's probably a good answer. So we might want at this point to start weighing the paths. Well, this path happened once out of 5,000 examples. Maybe it's a bug. And this is
Something I just realized. If you go back, so your notion of symbolic automata, one back to the previous slide, please.
Yeah.
So your notion of symbolic automata, the variable actually can take on the value of a string, not just a character.
So it can take on the value of any non-empty regular language, symbolic language. Yeah.
So that's what lets you do this multi-step compression.
Yeah. In fact, I mean, a loop can go here, a branch can go there.
That's why, for example, you didn't need to put a self loop. When you model B1, you don't need to make a loop because essentially that variable can capture a loop.
Yeah, that variable can capture anything. So. Okay. So I was saying we might want to weight our paths, which the implementation we have actually does. And then we can maybe not give you answers to your queries from paths that might be bugs. And now we can take the query that the user asks, like, what do I do around read, which translates to X read Y. What do I do around socket read? And give it to a known elimination to fill out and give me the assignment of X needs to be still a variable. And I'm renaming them just so it's less confusing. So Z and can read, and Y is can read and W. So I still don't know what's before and I still don't know what's after, but this is the best result I could give you. Now, prime. Prime is actually the implementation that came before the formal work. It's an implementation of this analysis for Java in Java. It uses Soot. It consolidates similar histories in a very heuristic manner. And it provides a comfy visual representation of the database and results of queries. It can be found on SourceForge. And it's a work by Alon Mishne, who's the grad student who came before me and already finished. It was benchmarked on most of the Apache Commons, on Ant, on some of the Eclipse APIs, on JDBC, and on WebDriver, which is the unit testing suite that Google works with. And WebDriver was also our benchmark for verification. So we know that we can both compress a large amount of results and use the database for verification. And this very uninformative benchmark results basically tell us that we used a lot of APIs for a large number of code snippets that came online, from online. And then what we did is look for the tutorial. Could we find a tutorial in our database? And usually if we tried to either use the database to rank examples as canonical or not, we got the tutorial very, very high, or to verify the tutorial, and we got it as correct. So what next? First of all, we want to start formalizing the probabilistic approach, which is what I was mentioning as weighing the paths to see if we can eliminate paths that are bugs because they're very, very infrequent. Since we'd like to use this as a wisdom of the masses sort of thing. Prime, the implementation, actually already does this, except you have to eliminate the very infrequent paths yourself. We'd like to come up with some better heuristics for the very, very inefficient things that we do. And we'd like to better handle explicit code elements. We'd like to have a conditional statement actually look like a conditional statement and not have to be proficient at reading these DSAs and say, oh, well, if it's the thing right before branching, then it's probably the condition, and I don't know which branch is the true and which branch is the false. The same thing with error handling code. I like to say this is work code and this is cleanup code that has to go in your finally block or it's a bug. Questions?
Questions?
Yeah.
The queries that you ask are what can go around, like a read, for example. But you might also want to know, what do I have to do before I do a read? Can you answer such queries?
Well, it depends. If you want I can take anything that you want to ask and turn it into a DSA. If you say, well, I know read has to be the last thing, then I'm going to turn it into a query where you have X, read, and an accepting state. And then you're going to get no result because you have no correct usage path that ends with read. Or I can say, well, I know I have to open and I know I have to close the socket, and I have no idea what to do in between. So I'm going to say open X and close and try to let the database open that, and I'll get either send or can read read.
But suppose I want to ask about read, and I want to find out that I need to open it first.
So if our database in this example was rather incomplete, it was from 2 sample programs, 3 methods in total. In the case of having a more complete database, and like I said, we aspire to a completely concrete database, then you're going to have, well, you have to initialize the socket, and then you have to connect, and then you have to, and then you ask can read, then you read, and then when you can't read anymore, then you close.
What query do I ask it to?
You still ask it X, read, Y.
But then I would get tons of results, right?
Well-
To consolidate them in my head. Or
Well, that's why we want to consolidate them for you before we start answering queries. That's why we want the most informative representative of our join result. But if you have more than one usage scenario that goes through read, yes, we're going to give you that. We're going to give you anything that we see as correct, which is, of course, why we want to start throwing out things that we see as incorrect.
So you basically want to give first the one that most people use, the scenario that most people use. That's the one you try to use.
Usually the scenario that most people use is going to be the one that's correct, because enough people have debugged their code and ended up with a correct result. Of course, you have incorrect examples that get copy-pasted around. And when you look at results of prime, you see that you have the path that happens for 4,000 code examples and the path that happens for 50, because 50 people copy-pasted a bug around from incorrect usage examples and propagated it forward. So that happens. But if you have such a big difference in the level of usage.
So is this for like proper use of APIs for generating documentation and stuff like that?
This is for proper use of APIs, and it doesn't quite replace documentation, but since we're real people in the real world, sometimes the documentation sucks. So
When you have the symbolic automata and you have 2 X's, they are unrelated, right?
now, if you have 2 X's in the same automaton, that's an equality constraint.
I see.
But if you have 2 X's in 2 different automata, then you can think of basically variable renaming to take place
Scope of variable
within the same
And
automata.
if it's 2 X's, then it means actually the same component appears twice.
Yeah.
Exactly the same one.
Like there's a configure method, and I call it both here and here.
So it's a non-regular language. No, it's regular.
It's regular.
You plug in the same fixed DFA in the end.
Yeah.
And then the language will find right. You just don't know what it is.
So the unification is a bit tricky.
Negation is probably
The unique.
What are the closure properties? I mean, I guess it's not closed under negation.
I actually don't know. We didn't look at that so much. So I can think about it and get back to you.
what about, I mean, you look at the names of the methods, although you alluded to some sort of alias analysis to begin with, but there are other parameters as well. So perhaps when you call open with certain parameters, you're allowed to do certain other operations and not others maybe. Do you have plans to extend it to treat such data as well?
Yes, but they're not very near future plans, unfortunately. I mean, the holy grail would be looking at, enum values, string constants, everything, anything that would basically allow us to also do synthesis in the end of, from this database, we actually give you code of what you should do. But there are a lot of obstacles before we even get near that. So.
One last question. So I saw in your slides the word abstract domain. So it means it's very concrete. So, but anyway, so in general, when you have an abstract domain, you have a corresponding concrete domain and then relation between the two. So what's the concrete domain here and what is the relation?
No, the concrete domain is what I showed at the very beginning with the code examples. The domain of concrete histories,
Okay.
which are, of course, sometimes.
So when they're incomplete, you imagine, okay, there can be all of them. Okay.
So-
and the relation between the two, what is it?
The abstraction, which I didn't talk about so much here, which was formulated by Sharon Shoham a few years back, the one that we use right now is called past abstraction, which is basically to say an incoming sequence of methods, either one method, two methods, three methods, or so on, are going to be unified. So one past abstraction will say any incoming f is always going to go into the same node, which will fold loops on itself.
So intuitively, you don't have a best abstraction, isn't it? It's not more a gamma that you have. You say this automata represents this set of things. We can take it offline, but so given, do you always get the best abstraction or not? Which I think is another way of asking, do you have a Colewa connection?
We do. I think I actually have the paper in my bag,
Okay.
Sharon's
Okay,
paper.
okay.
But it's not always the best abstraction. I happen to rather dislike past abstraction as an abstraction, and one of the things that we want to do is come up with a better one that also allows us to preserve more properties and look a little bit more like the control flow graph. So.
Thank you. So there are a couple of slots open.